So what we've learnt so far is that electrons are in shells around the nucleus. And the shells closest to the nucleus have the lowest energy, with the shells furthest away from the nucleus having the highest amount of energy. These shells are broken up into subshells. The first shell having one subshell called the 1s subshell, the second shell having two subshells, which are the 2s and the 2p, and the third shell having three subshells, the 3s, the 3p and the 3d. So the first shell has the 1s, the second shell has got the 2, as I just said, the third has got the 3, and the fourth, and from then on, has all of the s, p, d and f subshells. The s subshell has one orbital, which means it can hold 2 electrons, the p 3 orbitals, which means it can hold 6 electrons, the d subshell has 5 orbitals, which means it can hold 10 electrons, and the f subshell contains 7 orbitals, which means it can hold a total of 14 electrons. So this is what they look like, and this is the different amounts that can fit into each shell. And you'll need to watch the previous video if you're not sure about any of this. Okay, I want to talk to you a little bit about the shape of orbitals. Orbitals form different shapes, and the s orbitals form a ball shape, or a cylindrical or spherical shape. P orbitals are shaped like a dumbbell. So it's sort of like this, and they say a dumbbell because it's a bit like a weight, or a dumbbell weight. What we're talking about when we're talking about the shapes that the orbital forms is the fact that an electron can be in any position at any time. But if you were to take photographs of that electron at these random points in time, you would find that there are certain regions in which an electron will spend most of its time. And I'm going to show you a little video or a little animation which sort of explains that. So here are the 2 electrons that are floating around. You can see here that at any random point they can be in any position. And here we're showing a p orbital, and they're doing the same thing. What actually happens is that at different points in time, as I said, they can be in any position here. They're randomly moving. They can actually be anywhere in the entire atom. But the majority of their time they spend in these shaped patterns here. And this is due to its being in its lowest energy form. The same as with the s orbital here. They basically, if you were to form that position, they're basically in a spherical position most of the time. Okay, and the other orbitals, the d and the f orbitals, are a bit more complex. They can make lots of different shapes. So here's the p orbital here, the dumbbells. Here's the d orbital that I was saying that can be a bit more complex. You can get these donut rings forming. And the f orbital is just crazy. You've got a couple of donuts here with a few little bulges on the outside. But they're just the different shapes, and they've mathematically worked out these positions. But I just want you to be aware that they can form different shapes. Okay, valence electrons. These are the important guys. They're the electrons that are in the outside shell. So these are your valence electrons, the ones that are in the outside shell. The rest of these electrons are called core electrons. And here's just another example here. When you're filling up in order, remember that the 4 indicates the shell number. So these are your valence electrons. They are in the outside shell. Even though 4s has a lower energy than 3d, it's the 4th shell electrons as the outside shell that we're looking at for the valence electrons. And here's just another example. The periodic table is organised amazingly. There are 4 different blocks. This is your s block here. All of these atoms are filling up their s orbitals. This is your p block. All of these are filling up a p orbital, whether it's the 2p, 3p, 4p, 5p or 6p. This is your d block, the d orbital is being filled up, and these are your f block elements. So you've got your s block, which is your group 1 and your group 2 elements. The maximum number of electrons that can fit into an s subshell is 2 electrons. Group 1 has 1 electron in its s subshell, which it's filling up, and group 2 have 2 electrons in their s subshell. Let's look at the p block. how many electrons maximum can fit into a p subshell? 6 electrons. So the elements here are being filled. They're 1 in their p subshell, 2 in their p subshell, 3, 4, 5, 6, and so on. The p subshell is the one that's being filled up. The d subshell can fit 10 electrons. These are your transition metals. So in this column here, you've got 1 electron in your outside d subshell that's being filled up. 2 in the second, 3 in the third, 4 in the fourth, and so on. And lastly, you've got your F block. This can hold a maximum, the F subshell, of 14 electrons, and thus this transition element block is 14 spaces across, because this one, F shell, will hold 1 electron, 2 electrons, 3 electrons, 4 electrons, up to 14 electrons. If you look at a periodic table, you can now identify exactly which is the subshell that's being filled. For instance, here the 5s2 subshell has been filled. Here it's the 4d10 subshell that's being filled. Remember, the number at the front is indicating the shell number, so it's the 4th shell, the S subshell, and it has 1 electron in it. It's the 7th shell, the P subshell, and it has 1 electron in it. If you take note, you will see that these shell numbers generally refer to the period that the atom is in on the periodic table. So you've got period 1, period 2, period 3, period 4. You must be careful with the D and the F subshell, because remember, they start filling out of order after the S and the P. So for instance here, the 4s subshell will fill up completely before the 3D starts filling up. The 5s subshell will fill up completely before the 4D1, 4D2, and the 4th subshell continues to fill up. There's a couple of exceptions to the rule on the way in which the electron configurations are filled up. Let's have a look at chromium here. So, chromium should fill up in order, with the last two being 3D4, 4s2. However, if we have a look, we will see that chromium is actually 3D5, 4s1. And this is makes it a half-filled D subshell. So D can fit a maximum of 10, and chromium has decided it would rather have a half-filled subshell here and a half-filled subshell here than it would have a partially filled subshell. A half-filled subshell is more stable than a partially filled subshell. Let's have a look at another example of an exception. Copper. You would think, filling it up the way we've learnt, it would be 3D9 and 4s2. It's not. It is 3D10 and 4s1, because a filled D subshell is again much more stable than a 3D subshell with only 9 in it, or a partially filled subshell. So a subshell is more stable if it is half filled, such as this one, which is 5 out of a maximum of 10, or a filled subshell than a partially filled subshell. So these are two exceptions that you will find. Pretty much the rest of them follow the rule, or anything in the same groups as those. Okay, so you should be able to finish the booklet questions that I've given you now, and also the chapter 2 questions.